So on the board, we began from first principles with our definition of velocity, our definition of acceleration. We used some reasoning, and then we arrived at these first two equations, x equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. If you want some practice, you could take these two equations and combine them to arrive at this third equation. As a hint, I would say, notice that this equation does not have any reference to time in it at all. So somehow you need to take one equation and get rid of t. So in this course, as I said before, I want the things we talk about to make sense to you and to be natural to you. It's okay if the first day something is presented, it doesn't quite make sense, but take the time, think about it, really ponder it, practice the concepts, and I want you to arrive in a place where you cannot imagine the universe working in any other way based on just some first principles and starting definitions that we agree to. Now, a very common scenario for constant acceleration that we will consider is the scenario of free fall. We will define free fall as a situation in which gravity is the only thing influencing an object's motion. So other than gravity, there is nothing influencing the motion of an object. That means we ignore air resistance, we ignore wind, there's nobody pulling something down or pushing it up, just gravity alone. The equations for free fall are the exact same equations as the equations of constant acceleration that we worked with on the previous slide here. They're written a bit differently, but these differences are ultimately just cosmetic. For example, normally I like to say the horizontal direction is the x direction and the vertical direction is the y direction for 1D motion. So when I'm talking free fall, if an object is moving in the vertical direction, I'm going to use y naught and y for initial and final position instead of x naught and x. Ultimately, all I'm doing is I'm changing a label. I could move in the horizontal under constant acceleration, or I could move in the vertical under constant acceleration. These equations will not be affected whatsoever. So changing from x to y, that's just a cosmetic change. Also, if we are in free fall, we define free fall as the only thing influencing our motion is gravity. Well, that means the acceleration is the acceleration due to Earth's gravity. The acceleration due to Earth's gravity depends on the mass of the Earth and the size of the Earth. These are things that are constant and true no matter where you are on the Earth. As long as you're within a few tens of miles of the surface of the Earth, the acceleration due to gravity is going to be 9.8 meters per second squared downward. Now, I have downward highlighted because if we decide that up is the positive direction, and this is something I like to do, there is no fundamental reason why I must choose up to be the positive direction, but I like to say up is positive. So if we choose up to be the positive direction, and I remember Earth pulls us downward, then the acceleration due to Earth's gravity will be negative 9.8. I said in the first video in this chapter, things have a position, they move, sometimes they change their speed. The rest of the chapter is just being careful to make sure that you are being consistent with what you say. So if I say up is the positive direction, which is something I really prefer to do all the time, then that means the acceleration due to Earth's gravity is negative because Earth tends to pull me downward. Now, I'm going to add that sometimes instead of saying A for acceleration, if you're looking at other textbooks, books will sometimes use lowercase g when they're talking about gravity due to Earth and objects in free fall. I personally really do not like to do this. I would rather have A for acceleration, and if I know that I am using the acceleration due to Earth's gravity, I just then remember to write negative 9.8, the numerical value of Earth's acceleration, when we decide that up is the positive direction. Sometimes books will say g equals 9.8 and write negative g for Earth's acceleration. Sometimes books will say g is equal to 9.8, but then choose to have the positive direction pointing downward. There is nothing wrong with this choice, but I just do not like to do it. I would rather say up is always the positive direction, and that's one less thing I need to think about. So I'm going to be consistent with how I approach problems. If you were to use one of these methods on an exam, I will not mark it wrong. As long as your reasoning and your math is correct, you would be just okay. So, as an example problem, and the rest of this chapter is going to be example problems I work through on the board. Let's say there is a bear that is chased up a tree by a vicious cat, and when the bear is 7 meters above the ground, the bear loses its grip and falls towards the cat below. So the questions are, how long does it take the bear to hit the ground, and how fast is the bear moving when it hits the ground? So what I'm going to do is, to address this problem, the first thing I'm going to do is I'll draw a picture of this problem. So here's my tree, here's my bear, here's my vicious cat below. The next thing I'm going to do is I'm going to look at this picture and I'm just going to begin labeling it. So how do I want to set up my coordinate system? Well, I probably will want to have up being the positive direction. I said before, that is what I am comfortable personally working with, so that's what I'm going to choose. How high should ground level be? Well, there is no reason that ground level has to be a height of 0, but I want to have ground level at 0. If I wanted to, I could choose the bear to be at a height of 0, but once I make that designation, that would mean if the cat is 7 meters below the bear, that would mean bear is at a height of 0, cat is at a height of -7. As I said, there is no reason why I must choose ground level to be a height of 0. I am allowed to choose the bear to begin at a height of 0, but personally, I don't want to do that. I am most comfortable saying ground level is 0, so that's going to be ground level is at a height of 0. And I look at this picture, I think about it, and I realize, okay, ground level is 0. That's going to be the final position of the bear when it hits the ground. Based on this designation, I must be consistent throughout the rest of this problem. If ground level is a height of 0, then initial height of the bear is going to be +7 meters. Now, I'm just going to quickly mention, here I'm using y0 for y initial. Here I wrote y final instead of y, which I usually would have written. So I am mixing notations here. In future problems, I'm not going to do that. Now, acceleration pulls the bear downward. So acceleration due to gravity is going to be -9.8. 9.8 is the strength of the acceleration due to gravity, and I have negative because Earth's gravity is pulling the bear in the negative y direction. Is there anything else we know? One way I could think about that is I could look at these symbols here. I have initial and final position, y0 and y, v0 and v, a and t. Are there any other things we know that we could right away label in this problem? And the other thing I could label in this problem is the initial speed of the bear is 0. How long does it take the bear to hit the ground? That's like asking what is time? That's an unknown. How fast is the bear moving when it hits the ground? That's kind of like asking was the bear's final velocity, so that's an unknown. How can I justify this statement? I am claiming right now that the initial velocity of the bear is 0. What's my justification for that? Well, to think about it, let's imagine how fast is the bear moving a split second before it loses its grip? Well, as long as the bear is gripping the tree, it's not going to be moving. So before the bear loses its grip, it has an initial velocity of 0. After the bear loses its grip, gravity will be pulling it downward. But let's think about that. We could say the bear loses its grip, an infinitesimal moment before the bear loses its grip, it's going to have a velocity of 0. An infinitesimally short time after the bear loses its grip, we're claiming it has an initial velocity of 0. Well, sometime much later, let's say when the bear is somewhere down here. So it began falling, it still is not near the cat below, but it is falling, the bear will be moving. Well, at this point, the bear will have a velocity. Let's say the velocity is -2. I don't know what the final velocity is going to be. I'm just making up a number. I say -2 because it has a speed of 2 meters a second and negative because it's moving downward. Well, to go from 0 to -2, you can't just instantaneously be moving at 0 meters per second one moment and negative 2 meters another moment. Somewhere up here, you have to be moving negative 1 meter per second. Somewhere up here, you have to be moving negative 0.5 meter per second. Somewhere up here, you need to be moving negative 0.1 meter per second. And you will always be able to say, well, between the moment before the bear loses its grip and the moment after the bear loses its grip, it has to have gone through a smaller and smaller increment of velocity. I'm going to demonstrate this picture more on the board when I work through this example problem. But the split second, the instant the bear has let go of the tree, gravity is accelerating it downward, but gravity really didn't have any time to really get it moving in any appreciable amount of time yet. So the initial velocity is still going to be 0. So I'm going to end here. I will continue with this example problem on the board, work through some other example problems, and then we'll move on to the third chapter.